guys look at it.
No, it's all right. You can. I'm sure you can tell me. So DeBroglie then. What? So we've just had the photoelectric effect, which is waves acting as particles. So now we're going to prove that sometimes particles can act as waves. What's a typical? What is the characteristic feature of a wave?
It's a wavelength.
That it has a wavelength, and what does it mean if it has a wavelength? In terms of a wave propagating, a wave travelling through space. What do waves do sometimes that particles don't, or that you would expect particles not to? When they pass through things. So if I have a gap, oh, that's a nice colour. So if you've got a gap like that,
excitement.
If I had a wave, so if I drew a wave front coming up to my gap like that, what's going to happen?
It's going to diffract.
It's going to diffract. So diffraction is the key. Which means it's going to spread out.
It's not equal at all.
Yeah, all right. So technically that should be the same as that. To get maximum diffraction, what has to be the case?
The
gap has to be similar to the wavelength.
So if the gap is A and the wavelength is lambda, then to get maximum diffraction, maximum occurs when A is equal to lambda. So when your gap is equal to your wavelength. Happy?
Mm-hmm.
So that happens with waves. You'd expect that to happen with waves. Now the strange thing is that if I took a similar gap down here, oh, wrong colour, but never mind, you get the idea. If I took a similar gap down here and I shone an electron travelling through, and I put a screen here and I put one electron, then another, then another, then another, then another, instead of them all travelling and existing only in this focused area, they end up diffracting. So if you had a pattern over time, you'd get a scatter of electrons all along the screen. Now the point is, well, so what does that mean? So that means that the wavelength of the electron, whatever that must be equal to the gap size. Well, how do we discuss the wavelength of an electron? How do we discuss the wavelength of a particle? Well, what did we say that particle was doing? We had an electron that was moving. So, two things that the electron is doing. One, it's moving at a speed of v, so velocity v. So it's moving with a velocity v. What else does that have that a wave doesn't?
Mass.
Mass of m. And when you multiply mv together, what do you get? You should know this as a previous triple scientist.
Double science.
What equals mv? There's a physical property where you multiply m and v together.
I'm thinking
Momentum. So the momentum of this electron is equal to the mass times. Do you remember it now? It's equal to mass. Oh, that's quite depressing then, really, isn't it? So the momentum of the particle of this electron is mv. Oh, the maths teacher's happy. So you got
It's just not as defined as physics, that's why.
momentum is mv. So to get the wavelength of this particle, we take Planck's constant and we divide it by the momentum of this particle. All right. So for example, if we do an example, the mass of an electron, what did we just decide it was?
9.11 times 10 to the minus 31.
Good. And let's pick a velocity. Pick a velocity for an electron, relatively quick.
Oh god, choice. 1.2 times 10 to the 5.
Very good, fine. 1.2 times 10. I don't. Right, try again then. So what did we say? Oh, okay. So we're just doing an example. And what's Planck's constant?
6.63 times 10 to the minus 64. 34.
What's the units Planck's constant?
Oh god. Oh, I can do this. Hang on. So it's going to be joules per.
So joule seconds.
Joule seconds, yes.
What are we doing now? Right, so now we plug these in. Let's have a calculation. Anyone? Calculator?
Oh, okay. As you can see, you're always very prepared.
Yeah. Oh, the calculator magically appears out of nowhere. So what have we got here? 6.63 exponent minus 34 divided by... I realise I'm old school in that I use brackets. Everyone else...
Brackets rock.
Brackets make calculators safer. Can't just calculate otherwise.
Well, this is true.
And it breaks it up for you so you know you're doing it right.
Here we go. So the gap, so the wavelength of this electron would be 6.065 times 10 to the minus 9 meters, which what's that roughly the same as? When does this come up? When do these questions? What's the proof? Sorry, not the proof. What's the use of electrons having a DeBroglie wavelength?
How you can observe the diffraction pattern.
Through what?
Through a small hole.
Specifically, what do you get told about?
Oh, the space between
Fringes.
No. There's something in.
Graphite.
Yes, very good, graphite. So if we've got, for example, isn't graphite a polygon?
It's got 6 sides.
Something is a polygon? What's 6 sides? Hexagon.
A polygon
Hexagon.
just is a many side.
Yeah, that's right.
Are you sure you did a physics degree?
Yeah, tell me about
If
it.
you go back, I think you'd be entitled to a refund.
Cheers. You'd think.
I joke.
It's the love I get at school. So if we look at this atomic spacing in here, so our spacing between atoms is going to be in the region of, well, what is that roughly? What is atomic spacing roughly?
You're a chemist.
Oh, I should know this.
10 to the minus how many meters?
I really should know this.
Yes, you should. It's in the region of 10 to the minus 10 meters. But
Yes.
so what you would
Right.
do, if you were doing this in terms of an experiment, what's the one thing you're going to be able to vary? So wavelength is what you're trying to. So the one thing that you can vary is your velocity. What's the limitation?
You can't go faster than light.
Can't go faster than light. And when you start approaching light, what happens?
Things start to gain mass.
Things start gaining mass. So as this starts getting too big, as this approaches 10 to the 8, I mean we're in 10 to the 5 here, so we're all right. Once you start approaching 10 to the power of 8, this m value starts increasing, so it becomes more difficult to interpret. How could you count? Oh no, that's an A2 question. We'll come back to that some other time. Yeah, we'll come back to that some other time.
No, please don't.
No, it's fine.
Don't confuse me.
There's no point confusing you so close to the other. DeBroglie, have we look at the spec? Have we missed anything out?
No, that's pretty much it. That's all it's asking for.
Spacing, describing experiments, graphite.
Yeah, it doesn't even mention graphite.
Are you happy with? Are you happy with that? Is there anything else you need me to go over?
No, that's fine.